Welcome to ElectrAspirant, an assistance to electrical students for objective type exam preparation. And it is initiated by the Department of Electrical and Electronics Engineering, Christ College of Engineering, Iringalaguda. Now, in this session, we will be dealing with electromagnetics and we will see few of the Maxwell's equations and few number of objective type questions also. Now, let us see the Maxwell equations or four Maxwell's equations. One is from the total electric displacement through the surface enclosing a volume is equal to the total charge within the volume, and it is given by the differential and integral form. The differential form is del dot T is equal to rho by epsilon 0, and the integral form is surface integral E dot dA equal to 1 by epsilon 0 volume integral rho dV. The second one is regarding the magnetic field emerging through any closed surface is equal to 0, and it is given by del dot B equal to 0 because the divergence of magnetic flux density is equal to 0. Magnetic field never diverges, it always rotates itself, and its integral form is surface integral B dot dA equal to 0. Two more equations we will see. One is regarding the electromotive force and next is regarding the magnetomotive force. The EMF for electromotive force around a closed path is equal to the time derivative of the magnetic displacement through any surface bounded by the path, and actually it is coming from Faraday's law. So, del cross E is equal to minus dou B by dou T, that is the rate of change of magnetic flux linkages, and it is equal to the EMF induced actually, and its integral form is line integral E dot dl is equal to surface integral dou B by dou T dot dA, and the first equation is used for when the flux is changing. The flux is changing at a constant rate, and another is for when the conductor is changing and the flux is constant. And the last one we will see the magnetomotive force around a closed path is equal to the conduction current and the time derivative of the electric displacement through any surface bounded by the path. It is given by del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou by dou T of E, and line integral B dot dl is equal to surface integral mu 0 J plus epsilon 0 mu 0 dou E by dou T dot dA. In all the four equations, E is actually the electric field intensity in volts per meter, B is the magnetic induction or flux density in Weber per meter square, and J is the conduction current density in ampere per meter square. As a special cases, for static field, if the field is stationary, dou B by dou T is equal to 0, that is rate of change of flux is 0 because it is a static field. For a steady state current, actually J is equal to 0, that is dou B by dou T equal to 0 and J equal to sigma is equal to 0. And third one, for a perfect conductor, the conductivity sigma is 0, therefore J is equal to sigma E and is equal to 0. Now, let us see one of the objective type question. For an electric field E is equal to E0 sin omega t, what is the phase difference between the conduction current and the displacement current? This question can be dealt with using our basic informations, and equation wise also we can prove it. Using our common sense or our general basic informations, the displacement current is actually happening in the capacitor and conduction current is happening in the resistive circuits. So, resistance, current in the resistance and current in the capacitor, you know that current in the capacitor will be leading by 90 degree and the current in the resistor will be in phase with the voltage. So, the displacement is 90 degree. Thinking in that way, we will get displacement is 90 degree. But then using the equation also we can prove this thing. Let us take Maxwell's equation. Del cross H is equal to J plus dou D by dou T, where J is the conduction current density and dou D by dou T is the displacement current density. There is a total current density is J plus dou D by dou T, that is conduction current density plus displacement current density. Now J is equal to sigma E, that is all, plus D is epsilon E, therefore epsilon into dou E by dou T, where J is the conduction current density. Now it is in the problem, it is given as E is equal to E0 sin omega t. So let us take del cross H. Taking del cross H, sigma E is equal to sigma E0 sin omega t plus epsilon into dou E by dou T. So epsilon into, take the derivative, so their omega is also epsilon omega E0 cos omega t, and that is equal to sigma E0 sin omega t, that is a conduction current density, plus epsilon omega E0 sin omega t plus 90, because cos omega t is equal to sin omega t plus 90, that is a displacement current density. Now from here it is clear that the displacement current leads by 90 degree, and therefore the phase difference between the conduction current and the displacement current is 90 degree. So we will see another problem. An air condenser of capacitance 0.005 microfarad is connected to a DC supply of 500 volt, disconnected and then immersed in oil with an dielectric constant of 2.5. Energy stored in the capacitor before and after immersion respectively is. So A, B, C, D, 4 options are there. Our option, the correct answer is C, 6.25 into 10 raised to minus 4 joules and 2.5 into 10 raised to 4 joules. Let us see how do we get it, reach at it. Now let us see before immersion what is the energy stored. C is given to us 0.005 microfarad, V is 500 volt. Now energy stored E1 is equal to half CV square. So substituting the values, we are getting E1 is equal to 6.25 into 10 raised to minus 4 joules. So after immersing, what is happening actually? The only change is in the epsilon R. In the relative permittivity is being changed because the medium is changed. All other things remain same. So when the medium is changed, what is being changed? If epsilon R is changed, the capacitance will change. But the charge stored in the capacitor, already stored in the capacitor, will remain the same. The same charge will be there. Okay, same voltage will be there. The only thing which is changing is the capacitance will be changing. But the charge on the capacitor remains the same. Therefore, we can find out the charge Q is equal to CV. So we are for Q, we are getting it as 2.5 into 10 raised to minus 6. Now what is energy stored? Energy stored is equal to half Q square by Z1. We are getting this equation as half CV square in half CV square. Just change V. When V is equal to Q by C, therefore V square is equal to Q square by C square. Therefore we are getting it as C is equal to half into Q square by C1. And substitute those values, we will get it as 2.5 into 10 raised to minus 4 joules. That is how we are arriving at this answer. Now let us see yet another question. The capacitance of a parallel plate capacitor is given by epsilon 0 epsilon R A by D, where A is the area of each plate and D is the distance between the plates. Considering fringing field under which one of the following conditions is above expression valid. Now here actually in this question they are bringing actually a new concept, fringing field. So we should have an understanding of the fringing field, then only we will be able to answer. Normally the capacitance of a capacitor is given by C is equal to epsilon A by D. So epsilon is equal to epsilon 0 epsilon R. So epsilon 0 epsilon R into A by D is the capacitance actually. But that is not considering the fringing field. So let us see how we are explaining this one. Now what is the fringing field? From the figure you can understand that what is the fringing field. Directly which is moving between the plates, straight moving plates is the electric field lines. But the fringing field will be a bending field from plate to plate. that is a fringing field. Now, when the distance between the plate of a parallel plate capacitor is finite, if it is very near, there exists a fringing field. Fringing field, you can expect always a fringing field for a parallel plate capacitor, and then the formula C is equal to epsilon 0 epsilon r A by d, it cannot be valid over there. Now, when it can be valid for a parallel plate capacitor? Let us see, when A by d tends to infinity, the distance moves to infinity, the electric field lines are also straight. So, the fringing field will slowly vanish, and therefore also straight at the ends of the plate, and the fringing field does not exist. And therefore, the formula Z is equal to epsilon 0 epsilon r A by d is valid in the absence of the fringing field. So, that is how we are arriving at that answer. Now, let us see one more question. The potential distribution, we should understand that the potential is a scalar quantity. In electric field, the potential is a scalar quantity, that is a work done. So, potential distribution is given as V is equal to 10 y raised to 4 plus 20 x cube. If epsilon 0 is the permittivity of free space, what is the charge density rho at the point 2 0? So, of course, the answer is D, that is minus 240 epsilon 0. Let us see how we are arriving at it. In order to arrive at this equation, this answer, we will use Poisson equation. Let us take the Poisson equation. Del square V is equal to minus rho by epsilon 0. So, del square is actually the second derivative. Okay, second derivative. So, del is a differential operator. So, second derivative of operator. So, the second derivative, we will take the second derivative and substitute for V 10 y square plus 20 x cube is equal to minus rho by epsilon 0. So, that taking the second derivative, the 2 times derivative, we will get it as 20 into 3 into 2x plus 10 into 4 plus into y square, 3y square, that is equal to minus rho by epsilon 0. Now, we will substitute at point 2 0, we will substitute for x equal to 2, y equal to 0, then we will get as 20 into 3 into 2 into 2 is equal to minus rho by epsilon 0. So, that is rho is equal to minus 240 epsilon 0. So, that is all for the day. Thank you very much. We will meet again.